Hello, AP Calculus students. In today's lesson, we are going to look at the second derivative test and then try to identify what information determining a second derivative can tell us about the shape of a particular function that we are examining. Now, if we take a step back and look at just a first derivative, a first derivative is essentially just the rate at which your function is changing. And the rate at which your function is changing is an indication as to what the slope is. If we look at the second derivative is the rate at which the first derivative is changing. So if I were to try to describe in words what exactly a second derivative is, and I'll do it over here, we'll say that f double prime of x is an indication of how the slope is changing. So let's look at the two different scenarios. Let's say we find the second derivative of the function f of x, and we plug in a value of x, and it's something that's bigger than 0. If f prime of x, f double prime of x is a value that is bigger than 0, what that means is that the slope is increasing. Not necessarily the function itself, but the slope is increasing. So I'll show you a couple different scenarios where we can have a slope that is increasing. So I'll do it up at the top here. So let's say we have f double prime of x, and f double prime of x is greater than 0. So again, that means that your slope is increasing. Now, one way in which the slope could increase is if you just, I'm just going to draw part of just some kind of random curve. So we could have a curve that starts down here and it goes up like that. Okay, that definitely is an example of a situation where the slope is increasing, because from left to right hand side, if you were to draw tangent lines at various points, well, the tangent is very horizontal to start off with. And as you go further and further and further and further towards the right, the tangent line becomes steeper and steeper. So what's happening right here is the slope is becoming more positive. Okay, and almost underline that in red. Okay, that's one way where you can have the slope increase. Now, there's another way this can happen too. If I have a curve that starts up here and kind of flattens out, what ends up happening is if you look at the slope and going from the left to the right-hand side, is initially the slope is like a really big negative number, because if you were to draw a tangent line at the very left-hand side, okay, it's very steep and it's a negative slope because it goes down and towards the right. Now, as you start to make your way down the slope here, well, the slope becomes progressively less negative. So when you get to the very bottom, your slope's still negative because you're still going down and towards the right, but it's not as negative. And if you have a slope that's not as negative, it is actually technically still becoming more positive. So I'll say here, this is another way in which your slope can increase. Your slope becomes less negative. Now, whether you have the slope becoming more positive or the slope becoming less negative, in either scenario, your slope is increasing. Like maybe on the right here, you start off with a slope value that's negative 10, and then you end up with a slope value that's -1, well, because you're going from -10 to -1, your slope value is increasing despite the fact it is still negative. Now, let's look at the scenario where we have f double prime of x where it's going to be less than 0. So if f double prime of x is less than 0, that means that the slope is decreasing. And just like above here, there's two ways where this can happen. So we'll write down f double prime of x. We'll say it's less than 0. So the more intuitive way in which the slope can decrease is we can just draw a curve that starts like this and then it just drops down like that. Okay, that's definitely a decreasing slope. You start off on the side here, your slope is like a small negative number, and your slope just becomes increasingly negative as you go from the left to the right-hand side of the graph. So we'll say slope becomes more negative. And if it becomes more negative, the slope decreases. There's another way this can happen too. So we'll say or. I can also have a graph. It kind of has this shape right here. So in this graph, what happens is off the very start, you have a very large positive slope. Okay, your slope is going up and towards the right, and it's a big positive number. But as you start to go more and more towards the right, the slope starts to flatten off. So that positive slope is actually starting to decrease in value. So what's happening on this curve as you go from the left to the right-hand side is that your slope becomes less positive. And if your slope becomes less positive, or if your slope becomes more negative, those would be scenarios where your slope is going to decrease. And that happens when your second derivative is less than 0. If your second derivative is bigger than 0, then it means your slope is going to increase. Now, whether the slope is increasing or decreasing, they are attached to very specific words. So the first one we're going to look at is a word that's referred to as concave up. Okay, I'm just going to draw a little grid over to the side here to kind of show you the difference between the two of them. Okay, concave up just means you have a, like, what's the best way to explain this? Like you have a curve that kind of like starts down here and then it goes up. Now, if you were to take this curve and you were to kind of like extrapolate and just draw the other side of like this and try to draw it as a parabola, it would look a little bit like this. Okay, this is referred to as concave up. Now, there's technically two ways you could draw it. Like you could have concave up would just be you have an arm that starts to have your slope become more positive, or it could be this left arm here where your slope becomes less negative. Okay. Either way, though, if you just take the portion of the curve and you just extrapolate it to get a full parabola, concave up would just mean that the extrapolated parabola opens in an upward direction. So Concave up, I don't know. This is like the way I was reading like somebody else describe it. Like a concave up graph is kind of like the graph is smiling. So we'll say it's like smiling. Okay, so it's kind of got like this shape to it right here. Now, if you look at concave down, okay, concave down can have one of the two shapes we identified if the second derivative is going to be less than 0. So if I draw that over to the side here, okay, let's just pick the first one. So the first one is this graph. That kind of goes down like that. Now, again, if you take that curve and you draw an extrapolated parabola, it would actually give you the other alternative. So the first alternative is the arm where you kind of start and you go down and towards the right. And the other alternative is when you start at the bottom and you go up and towards the right. So whether it's this curve that goes down towards the right or down and towards the left, as long as that extrapolated parabola opens downward, we refer to that as being concave down. And what exactly is concave down like? It's like you're frowning. I don't know. If you want to use that as a way to memorize it, go ahead. It's a little bit silly, but that's okay. Concave up. You just take one portion of this parabola that kind of like smiles. Concave down, one portion of the parabola where you do have that frown. Now, in terms of what exactly an inflection point is, and we define this back in Math 30-1. So I'll just quickly like draw an example of like what an inflection point looks like back from 30-1. So let's say we have an inflection point that's on the origin of the graph. So what this would look like is you'd have a graph that maybe starts down like this, hits this point. Now it looks like you might be at this point about to hit a local maximum. But instead of it being a local maximum, the graph goes back down, it kind of changes a little bit and it goes up like this. Now, in terms of what exactly is happening is at an inflection point, you have a change in concavity. So if we start from the left and go all the way towards the right here and try to identify how the concavity is changing, well, we start at the bottom left, hit the origin. If I were to draw the extended parabola, okay, the extended parabola would go down. So on the first portion right here, the part on the graph that's in quadrant number 3, the graph would be concave down in that portion. And if we go up to the top of the graph, and we draw the extended parabola at the very top of the graph, just going to take this arm, extend it. That turns into concave up. So anytime we have a change in concavity, whether you go from concave down to concave up or concave down to concave up, we refer to that as being an inflection point at that specific point. Okay, now we've kind of described the connection between the second derivative and the concavity, and also defining what an inflection point is. We can describe the second derivative test. Now, this will make more sense. We get into an example in just a moment here. But what this says is that suppose that you can calculate the second derivative. So f prime of x is a continuous function near c. It says if f prime of c is equal to 0. So that's a critical point. Okay. So a critical point on the first derivative where you have a point where you're changing from the graph increasing to decreasing or decreasing to increasing. And then if you go ahead and you take the second derivative, if the second derivative has a value that's greater than 0, you're going to have a local minimum at that point. If the second derivative has a value that's going to be it's going to be less than 0, it's going to be a local maximum. Okay. Now we can make sense of this though. Okay. So let's look at this. So let's say we have this scenario, like f double prime of c is greater than 0. That's a critical point. So if I were to draw that, okay, a local minimum would be a graph that looks something like this, okay? So a curve that's that, and we'd say that we have our local minimum at this point, okay? At this point, we're like x is equal to c. Now, if you look at it, whether you're on the left-hand side of the graph or left-hand side of the critical number, or you're on the right-hand side of the critical number, the slope is always trying to become more positive. So going from left to right, you start off with a large negative slope, but as you make your way towards that critical point where you have your local minimum, that you're you're starting to get a slope that becomes less negative. And as the slope becomes less negative, it's becoming more positive. Once you hit the critical point at the local minimum and keep going, well, now the slope is beginning to become increasingly positive. Okay. And again, that follows the shape of having, as you can see right here, this shape is concave up. So if you have a critical point, that's a local minimum, then the second derivative of that point is going to be greater than 0 because it means even at this point, now the slope here at this point is actually equal to 0, but the second derivative is about how your slope is changing, okay? And even at that point, that slope is continuing to change in a positive direction because at this critical point right here, it's changing from having a slope that's negative to now a slope that's being positive. And we could do the same thing for a local maximum. If you draw a graph of like what a local maximum would look like, okay, perhaps something like this right here. So with the first derivative test, okay, a local maximum would be at this point, x is equal to c. And if you start on the left-hand side of the graph and you start making your way towards the right-hand side of the graph, the slope starts off as being a large positive number. But as you make your way towards the local maximum right here, the slope becomes less and less positive. And then as you hit the critical point, the slope is now negative, but it becomes increasingly negative. So no matter what you're doing here, so again, here's my local max. Again, this was a local min. Your slope is always becoming more negative. And that'll happen if that portion of the graph is concave down. All right, let's get into some example problems. So it says, determine the open intervals on which the graph f of x is equal to 6 over x squared plus 3 is concave up or concave down, and then state any of the inflection points. Okay, so the first thing I wanted to figure out whether it's concave up or concave down, we have to get to determining what the second derivative is. But before I can get the second derivative, I need to know what the first derivative is. So let's rewrite this in a form where I can actually apply one of the derivative rules. So I'll write down f of x as being equal to 6. And then I have x squared plus 3. And we'll write that to the power of negative 1. If I go ahead and take the first derivative, so we'd have f prime of x would be equal to, we'll move that negative 1 in front, so it'd be negative 6. And then it'd be x squared plus 3, all to the power of negative 2. Apply the chain rule on the x squared, which is the 2x. And then this would give me f prime of x is going to be equal to negative 12x. And then x squared plus 3 all to the power of negative 2. Now, I'm just going to figure out what the critical value is at this point, or the critical value is based on the first derivative. So the critical value is, let's rewrite the first derivative and just without the negative exponents, we'd have f prime of x would be equal to negative 12x divided by x squared plus 3 all squared. In terms of the critical numbers for the first derivative test, there's two possibilities. You're either looking at what's the value of x you can plug into the denominator that makes the function undefined. Now, for this one here, that's not possible. Like if you have x squared plus 3, there's nothing you can do to make x squared plus 3 equal to 0 because you're squaring the x. So that's not a possibility in terms of identifying a critical point. So we'll say no possible solution. The other way is you take the first derivative and you just set it equal to 0, because that just means where the slope's going to be equal to 0. And the slope will be equal to 0 at a point where you're going to have like a local minimum or a local maximum. So we said f prime of c is equal to 0, which would be equal to negative 12c all divided by c squared plus 3 all squared. Now, the way to solve this is you just set the two numerators equal to each other. So if we have 0 is equal to negative 12c, then it would tell me my critical point is going to be c, which is equal to 0. Okay, now I need to figure out what the second derivative is. Again, the whole idea is we're trying to figure out where is the graph concave up or concave down, and then we're trying to figure out the inflection points. So we'll go ahead and do this now. So we'll figure out f double prime of x. This is going to be a bit ugly to do. Now, the equation I'm going to base it on is going to be the one that is going to be written right here. Actually, no, check that. We'll do the one that's written in this form. So I'm going to have to use the quotient rule. Okay, so what this would look like is f double prime of x would be equal to, so we take the derivative of negative 12x, so that would just be negative 12. That's easy. And then hold the denominator constant, so x squared plus 3 all squared. Subtract. Second time through, we keep the numerator constant, negative 12x, and then it's the derivative of the denominator, so we bring the 2 in front, multiply by x squared plus 3, and then multiply by 2x using the chain rule. And then we have to divide this all by the denominator squared. So this would be x squared plus 3 all squared. And we're going to square that. Okay, let's try to simplify this a little bit. So I want to try to pull out some common factors. This is actually an easier way to do it compared to multiplying everything together. So if you look at this to begin with, what you can do is this negative here and this negative times a negative would just be a positive. So that would just be adding a positive here. Okay, now there's a few things I'm going to try to factor out. So let's try to factor out the biggest coefficient I can pull out. So biggest coefficient I can pull out is out of this first term, the biggest thing I can pull out is a negative 12. Okay, so I'll pull that out. Now I also have this x squared plus 3 factor, So I can pull out an x squared plus 3 just to the power of 1. Oh, no, wait. Yep. Okay, x squared plus 3 all to the power of 1. And now let's see what we're left with in brackets. So in brackets now, I would be left with We pulled out the negative 12. We pulled x squared plus 3 to the power of 1. So that would just leave me with x squared plus 3. And then we pulled out negative 12. So that would leave me with, because that was positive, so it's going to leave me with a negative for that one. And then we got to combine some of these coefficients together. So we pulled this 12 out here. But we still have the 2 times the 2x left. So that would be left with minus 4x. And then the x squared plus 3 has been pulled out. And then we'll divide this all by x squared plus 3. And that's going to be raised to the power of 4. Now, that's going to simplify a little bit, because what you can do is I can cancel this one on the top and then take this exponent and turn it into a 3. And then what I would have is f double prime of x would be equal to let's see here. I feel like I might be missing something. Let me double check. Oh, there's an x times an x here. Sorry, this should be 4x squared. Yeah. Because, yeah, x times that x. Which means that in brackets here, we can actually simplify this. This would be x squared plus 3 minus 4x squared. So that would be negative 3x squared and then plus 3. So we'd then be left with negative 12. And then in brackets, I would have negative 3 x squared plus 3, all divided by x squared plus 3, all cubed. And then out of here, you can pull out a negative 3. So if you pull a negative 3 out of the top, I'll just box what I'm pulling out here. So out of the top here, I can pull out a negative 3. And then this would be equal to negative 12. Pull out the negative 3. And then in brackets, I would be left with x squared minus 1. All divided by x squared plus 3, all cubed. And then we have what my derivative would then be. So this would then be equal to 36, and then x squared minus 1, and then divided by x squared plus 3. And then we're going to raise that to the power of 3. Now, after I've done this, what you then want to do is you want to find a second set of critical numbers. So I'm going to say find. But we're going to do this based on the second derivative. Okay, now, once again, you look at the second derivative function, there's the critical numbers would be what are the values of x that make the function undefined. Again, you can't do that because there's no way to make the denominator so it's 0. So the other way would just be taking the second derivative and setting it equal to 0. So we'll just say here, we're going to set f double prime of x is equal to 0. We'll call that f double prime c. Now, when we do this for the first derivative, when we set the first derivative, f prime of c is equal to 0, that tells me the intervals, where the function is increasing or decreasing. When I do this for the second derivative, where I take f double prime of c and set that equal to 0, that's not necessarily telling me where the function is increasing or decreasing. What it's telling me is we're using it to determine the intervals of concavity. Concavity, concavity, I don't know how to say it. Okay, that's for the second derivative test. So if you take f double prime of x and set it equal to 0, that gives you the intervals of concavity, as opposed to for the first derivative test that tells you the intervals where you're increasing or decreasing. Okay, so let's figure that out here. So if we plug in f prime of c, we then have, so f double prime of c would be 0, would be equal to 36. And then we have c squared minus 1 over c squared plus 3, all to the power of 3. And again, I'm going to figure out the solution to this, you just set the numerator that's equal to 0. So there's two possible critical numbers here. You can either plug in c is equal to positive 1, and then 1 squared minus 1 is 0, or negative 1, and then negative 1 all squared minus 1 is also equal to 0. So you'd have c is equal to plus or minus 1. Okay, I'll come back to this note in just a moment here when we talk about the points of inflection. Okay, now, what I'm going to do is I'm going to make an interval chart based on concavity now. So we'll do this. So we'll do an interval chart based on the critical numbers. So we'll say interval. There's going to be 3 of them. So one interval would be when x is less than negative 1. One interval would be when x is bigger than negative 1, but less than positive 1. And one interval will be when x is greater than positive 1. Now, my second column is going to be the sign of f double prime of x. So what this means is for this interval, we'll pick a number that's less than negative 1. So maybe that's negative 2. And we're going to plug it into the equation for the second derivative. And we're going to see whether the second derivative is a positive or a negative number. Well, it might be the easiest just to plug it in right here. So let's think about this for a moment. If you were to take negative 2 and plug it into the equation up here, well, negative 2 all squared would be positive 4. 4 minus 1 is positive, times 36 is positive. And it doesn't matter what you do to the denominator is always going to be positive, which means that the sign of f double prime of x when x is less than negative 1 must be a positive number. Now, when you're in between the interval negative 1 to 1, well, the easiest number to plug in is 0 right here. So if you're to take this 0 and plug it into the second derivative equation, 0 squared minus 1 would be a negative. Okay, it'd be negative 1. Negative 1 times 36 would be negative 36. And that would be, again, plugging 0 into the denominator is still going to be positive. So you'd have a negative divided by a positive, which would be a negative. And then the interval where x is bigger than 1, if you plug in, for example, 2, well, it would just lead to the exact same scenario if you had x is less than negative 1, which would have an f double prime of x sign that's going to be positive. Now, remember, the sign on f double prime of x tells me what the concavity is. So we can then just summarize as follows. If f double prime of x in a specific interval is a positive number, it means that the graph is concave up in that interval. If f double prime of x is negative in an interval, it means that it is concave down. If f double prime of x is positive in a specific interval, then it's going to be, again, concave, up. Now, I'll show you what the graph looks like at the end, even though we haven't quite got to the point where we're ready just to sketch this without the use of a calculator, but we're getting pretty close to being able to do it. But this essentially answers part of the question. So part of the question just said, what are the intervals of, which intervals are we concave up or concave down? Well, the chart nicely summarizes that, okay? So if x is less than -1, concave up. If it's between -1 and 1, it's concave down. And if it's greater than 1, it's concave up. It also wants me to identify points of inflection. So points of inflection are going to be the points where you have a change in your concavity. So here, specifically, if you compare these two intervals, okay, you're going from concave up to concave down. Okay, where does that occur at? It occurs at the critical number, x is equal to -1. So you're going to have one inflection point at x is equal to -1. And then here, if you go from this interval to the next one, again, you have a change in concavity. You're going from concave down to concave up. So you'd also have an inflection point at x is equal to +1. And we can quickly determine the coordinates of this. So if you want the coordinates of the inflection point, you have to plug it back into the original equation. So plugging back into the original equation for your points of inflection. So if we had f -1, and we plug it back into the original equation to get what the corresponding y value is, this would be 6 divided by -1 all squared plus 3, which would be 6/4, which is equal to 3/2. So one of your points of inflection would be -1 and 3/2. If you find the other point of inflection, so that's at x equals +1, it's going to give you the exact same thing. So it would just give you 6 divided by 1 squared plus 3, which would be, again, 6/4. And that's equal to 3/2. So this would then be 1, 3/2. Now, if you're wondering what exactly does this graph look like, well, I could just quickly sketch it up here. Okay, I got a bit of space just to do it. So let's draw like the x-axis. Let's draw the y-axis. Okay, and the graph looks something like this. It has a horizontal asymptote on the x-axis that it kind of like comes up to a local maximum here. Let's draw the local maximum a bit better. And then it kind of drop step back down like that. Now, we already identified that there was a critical point with the first derivative test at x is equal to 0. And we could have actually proved that by setting up a chart where we have the increasing and decreasing intervals, but it wasn't something that the question asked for, so we didn't need to do it. Now, in terms of the points of inflection, though, so if I were to label this on the graph here, okay, so you would have like a point, this might be x is equal to -1. And this right here might be where x is equal to +1. And what's happening is in this section, think of it as like, if you take this part of the curve, it'd be a parabola that opens upward. So this section right here is a part of the graph that will be concave up. If you take this interval between -1 and +1, well, that's a portion of a parabola where it's opening downward. So this entire portion here is concave down. And then this portion, once again, you have a portion of the parabola where it's opening upward. So that would be concave up. Now, if you're wondering why did we do this, like set f double prime of x equal to 0 to figure out the critical points for the intervals of concavity, well, essentially this is what's happening. When you have a point where you have an inflection point, so let's say when f double prime of x is equal to 0, for a very brief instant, the slope stops changing. So it's neither increasing or decreasing for a brief moment. And that's what's happening, because at a point of inflection, like what's going on? Well, your slope's no longer continuing to increase or continuing to decrease. It's actually changing whether it's increasing or decreasing at that point. So at the point of inflection, it's almost like it doesn't know what it's doing. Okay. So for like one brief instant, f double prime of x is equal to 0 because the slope isn't changing for a moment. And then right after you're past that point, then you have a change in concavity. Okay, let's do a few more of them. All right, it says determine the open intervals on which the graph of f of x is equal to x squared plus 1 over x squared minus 4 is concave up or concave down, and then state the inflection points. Okay, so to figure out again whether it's concave up or concave down, we have to get to the second derivative. Okay, so let's figure out the first derivative to begin with. So we have f prime of x, and we'll use the quotient rule again, would be equal to, first time through, derivative of x squared plus 1 is 2x. Multiply by the denominator, held constant, x squared minus 4. Subtract. Second time through, we hold the first one constant, so x squared plus 1, and then derivative of the second one, which is 2x. And then we divide this all by x squared minus 4, and we're going to square the whole thing. Okay, this time I'm actually going to just use distributive property and see what we can combine. So this would be equal to 2x cubed minus 8x minus 2x cubed. So that's nice. The 2x cubes go away. And then negative times positive 1 times 2x would be negative 2x. And then that's all divided by x squared minus 4 all squared. Okay, the 2x cubes go away. And this would leave you my first derivative. That would be equal to, we would have negative 10x over x squared minus 4 all squared. Now, we don't really need to do this because, again, we're just trying to figure out the intervals of concavity, but just because I want to show you what the graph looks like. Actually, I don't think just because I want to show you what the graph looks like quickly at the end, I will just figure out the critical points for the first derivative. So again, the critical points of the first derivative are values of x that make the function undefined. So for this one right here, we actually do have values of x that can make the denominator undefined, which is if you plug in positive 2 or negative 2, then that's going to give you the denominator. It's undefined. So here, your non-permissible values are x cannot be equal to plus or minus 2. Okay, those are going to be a couple of your critical points. Now, again, critical points might be points where you have a local max or a local min, but maybe not, okay? And then the other way is you can also take the first derivative and set it equal to 0. So if we do that, this would then be equal to negative 10c, all divided by c squared minus 4, all squared. And again, to figure out the critical values for this is basically just set the numerators equal to each other. So it's pretty obvious. The value of c, which would make the first derivative equal to 0, would just be c is equal to 0. Now, if you wanted, you could use those values to do an interval table where we could identify where the function is increasing and decreasing, and then immediately identify local mins and local maximums. But that's not really what we're interested in here. Okay, so we're going to find the second derivative. Okay, so we take the second derivative of this function. So I have f double prime of x would be equal to derivative of the top is going to be negative 10. And then we have x squared minus 4 all squared minus, keep that second function constant, negative 10x. A derivative of the second function. Okay, this gets a bit more complicated now. So you have to bring the 2 in front. Okay, then it's x squared minus 4 to the power of 1. And then use the chain rule, derivative of the inside, 2x. And then we divide this all by that denominator squared. So it's going to be x squared minus 4 all squared. And then we're going to square that whole thing. Okay, let's try to clean this out here, or clean this up a little bit. So maybe I'll do that. So maybe it'll make it easier to see the factors you can pull out. It might have been hard for me to see in the last one, so I was kind of getting a bit ahead of myself. So I'm not going to use distributive property in this first part. We'll just write down negative 10, and then x squared minus 4 all squared. We'll clean this portion up though. So negative times a negative would be a positive. Okay, 10x times 2 is 20x. 20x times 2x would be 40x squared. And then we have the x squared minus 4. And we're going to divide that all by, this is just going to power of power roll to be x squared minus 4 to the power of 4. Okay, now out of the top here, the biggest coefficient I can pull out is going to be a negative 10. So I'll pull that negative 10 out of the negative 10 and the negative 40 here. And then I can pull out an x squared minus 4 to the power of 1 out of those two x squared minus 4s. So then this would look like we'd have f double prime of x would be equal to, pull out that negative 10, pull out that x squared minus 4, and then I'd be left with in brackets just a single x squared minus 4. And then we would have negative 10 divided by 40x squared to be negative 4x squared. And then that's all that's left there because we've pulled out the x squared minus 4. And then we divide this all by x squared minus 4 all to the power of 4. Okay, and now I can cross some things off here. So this x squared minus 4 on the top can cancel, get rid of one of those exponents. And then I can write down my second derivative as being f double prime of x would be equal to, we would have negative 10. And then this will be x squared minus 4x squared, which is negative 3x squared, minus 4 divided by x squared minus 4 all to the power of 3. Let's pull out a negative out of this, this factor here. Okay, so if we do that, then this would just, it would turn everything to being positive. This is going to be nice because we're going to have to plug x values in for the intervals to determine whether f double prime of x is positive or negative. So this would then be equal to, I'd have, just be pull a negative 1 out, return that to positive 10. So you'd have 10, and then you'd have 3x squared plus 4 all divided by x squared minus 4 all to the power of 3. So that's my, yeah, that's going to be my second derivative. Okay, now we need to try to figure out what exactly is the critical numbers. So let's do that. So first of all, if I look at this right here, in terms of the second derivative, x cannot be equal to plus or minus 2. Okay, so you'd have some critical numbers that would just be plus or minus 2. Okay, so let's go ahead and we'll just underline that for now. Okay, now the other one is we would just set f double prime of x equal to 0. We'll call that f double prime of c. So that would be equal to 10. And then 3x squared plus, or 3c squared, I should say. 3c squared plus 4 over c squared minus 4 all to the power of 3. Now, if you look at the numerator here, if you take 0 and you set it equal to 10, 3c squared plus 4, there is no solution again, because there's you would just be setting 3c squared plus 4 equals to 0, and there's no way that you can actually make the 3c squared term negative to offset the positive 4. So there's no solution for that. So again, you're trying to get 3c squared plus 4 cannot be equal to 0. So there's no solution for that. Okay, so let's do our intervals of concavity now. So we'll say, so we have interval. Do you know what? I'll do it over at this side here so we have a bit more space. Okay, so I've got interval. Okay, my critical numbers for concavity are plus or minus 2. So we'll have 3 intervals. So we'll have x is less than negative 2. We'll have negative 2 is between x and is between 2. And we'll have x is bigger than positive 2. And we want to identify what the sign of f double prime of x is. And then we want to identify what the concavity is. And then based on the concavity, we can then identify inflection points. Okay, so let's start off by plugging into so again, here's my second derivative. Okay, we'll plug in a number where x is less than negative 2. Now, you can totally ignore the numerator at this, because no matter what, the numerator is always going to be positive. So it's a matter of plugging in a value of x that's less than negative 3 into the denominator and then seeing what sign we get. So if I were to plug in, for example, negative 5, well, negative 5 all squared would be 25. 25 minus 4 is a positive number. A positive number cubed would just be a positive number. So that would be positive, which means that it's going to be concave up. Okay, between negative 2 and 2, again, we're just ignoring the numerator because it has no effect on the actual sign. So if you plugged in x equals 0, it'd be 0 squared minus 4, which is negative 4. Negative 4 cubed would be a negative number, so that's negative, which means in that interval, it's going to be concave down. And if x is bigger than 2, it's the exact same scenario as if it's less than negative 2. If you picked like x equals 5, 5 squared is 2, minus 4 is 21. 21 cubed definitely gives you a positive number. So this is also going to be concave up. Now, when you look at this, it seems like I have 2 points of inflection. So when you go from this interval to this interval, that occurs at a critical number where x is equal to negative 2. And then when you go from this interval to this one, same thing. That seems to be an inflection point that's going to be at x is equal to positive 2. Now, these actually aren't inflection points because if you go all the way back up to the original graph, well, the original graph already has non-permissible values if x cannot be equal to plus or minus 2. Those are vertical asymptotes, okay? Not inflection points. And I'll show you what the graph looks like for this. So we'll say x equals plus or minus 2 are vertical asymptotes, not inflection points. So there actually are no inflection points on this graph. Now, if you're wondering, what does the graph actually look like? Okay, well, just let me sketch it at the top here. So let's do an x-axis. Let's do a y-axis. I'll draw my points where I have my vertical asymptotes. So we'll say this is -2, +2. I'll just do that with a dashed red line. We'll kind of go up like that, go down like this, go up like that, down like this. Okay, here's what my graph looks like. I'll do this in green. And again, we're going to go through some more steps of how we can sketch this by hand. But what the graph would look like is here. You have a horizontal asymptote of 0, which should go up like that. Okay, that's concave up. Here, you would have a graph that kind of does this, and you have a local maximum, which, by the way, this c equals 0 for the first derivative test, that would actually be the point where you have the local maximum. You can see that because when x equals 0, you do have that local maximum. But again, we're just looking at concavity here. So this would be concave down. And then the other portion of the graph looks something like this. And that is also concave up. So even though you switch from concave up to concave down and concave down to concave up, yeah, usually an inflection point is where you have a change in concavity, but not if that point's a vertical asymptote, and those points are vertical asymptotes. So this particular graph actually does not have any points of inflection at all, okay? Because those the points that we think are inflection points are in fact vertical asymptotes. Okay, let's do one more here. So the same thing, just have a different function. It's an exponential one. I want to figure out the intervals where the graph is concave up or concave down. So again, as soon as I start asking about that, that's going to be where you need to, that's going to be where you need to do the second derivative test. Okay, so let's figure out the first derivative. So we have f prime of x would be equal to, okay, first times through, this is going to be the product rule. So we'll take the derivative of x, which is 1, multiply by e to the power of x. And then you're going to add x. Derivative of e to the x is just e to the x. I can factor out a common e to the x, and then I just have f prime of x will be equal to, pull out an e to the x, and then I would have 1 plus x. Okay, now we don't really need to get the critical points for we don't really need the critical points to figure out concavity, but again, I'm just going to just calculate it just to try to figure this out. So there's no denominator, so there's no points where like you can plug in an x value to make it undefined. So it would just be a matter of where is f prime of c equal to 0 at. Okay, that would be e to the power of c, and then 1 plus c. So using the zero product rule, there'd be like technically two solutions. So it'd be like when e to the power of c equals 0, and then when 1 plus c is equal to 0. And then that's going to be your second solution. Now, there's nothing you can plug in for an exponent right here that's going to make e to the power of c equal to 0. There's no value of c that's going to make that true. So we only have a single critical number, and that single critical number would just be if you plug in c equals -1 to that second factor. So like I said, we don't need to do this, but when I just show you the graph at the end, it's just helpful to like identify, yeah, I've actually got like a local min or a local max at that point. But let's figure out the second derivative. Okay, so f double prime of x. So we're going to do it based on this equation. So again, we have to use the product rule. So first time through, e to the x stays, the derivative of e to the x is just e to the x. The 1 plus x stays the same. Second time through, e to the x stays the same. And you multiply just by the derivative of 1 plus x, which would just be 1. So what I'll do here is I can pull out a common e to the power of x, and that would leave me with in brackets. So if I pull out e to the x from the first set, I would have 1 plus x. Pull e to the x out from the second portion, you'd have plus 1. Therefore, my second derivative, you'd have f prime of x would be equal to, and I would have e to the power of x, and then it would be x plus 2. All right. Now, I want to figure out for the intervals of concavity, I need to figure out what the critical points are. So again, there are no points, values of x you can plug in that'll give there's no values of x you can plug in that are going to give make the function undefined. So what I immediately do then is we're just going to set f double prime of c equal to 0 to find intervals of concavity. Okay, so if I do that, so f double prime of c is equal to 0. This would be e to the power of c multiplied by c plus 2. And just like above, if you set e to the power of c equal to 0, there's no value of c which can actually make that equal to 0. And then the other solution would just be plugging in c is equal to -2. So let's go ahead and make our interval chart now. So we'll say we have our interval. We'll also have 2 of them. Okay, so if x is less than -2, and when x is greater than -2, okay, we want our sign for f double prime of x. And then we also want our identify the concavity. Okay, so we're basing it on this equation right here. Okay, now I'll just show some work over to the side here. So let's say that x was equal to, I'll just pick -3. So pick a number that's less than -2. So that would be e to the -3, and then it would be -3 plus 2. Again, I want to identify whether that's positive or negative. So what I'll do is I'll take the e to the -3 and write it at the bottom. So I'll write it as e to the positive 3 on the bottom there. And then -3 plus 2 would be -1. So -1 divided by a positive exponential base to the power of 3 would just be a negative number. Now, if we plug in, if x is bigger than -2, I'll just plug in x is equal to 0 because that's the easiest thing to do. So plugging that in there, it would just be e to the z power of 0, which is 1. And then 0 plus 2 is a positive number, so it would be positive. Therefore, we'd have concave down. And we'd have concave up. Okay, we have a change in concavity. So you're going from concave down to concave up. So this is a candidate for a point of inflection as long as x equals -2 is not a vertical asymptote, and it's not, because that's not a non-permissible value on this graph. So we can say x equals -2 is a point of inflection. Sorry, I don't know if I said point of inflection before, but yeah, it's a candidate for a point of inflection. And it is a point of inflection as long as that point is not a vertical asymptote. Okay, well, we need to figure out the y coordinate as well. So let's go back to the original function, just plug in x equals -2. So we'd have f of -2 would be equal to -2 times e to the power of -2. We're not actually going to calculate it. Okay, it would just be -2 over e squared. So your point of inflection would just be -2 and 2 over e squared. Now, if you're wondering what this graph looks like specifically, okay, we'll take a quick look at it. Okay, so let's draw an y-axis, draw an x-axis, and try to sketch this as best as I can. Okay, let's look at that critical point for the concavity. So that's going to be when x is equal to -2. Okay, and then what was the critical point for the first derivative? It was -1. Okay, so what the graph looks like here is it kind of starts off as like a horizontal asymptote of 0. Okay, it keeps coming. And then kind of like dips down. It hits this point, and then kind of goes up like that. So a -1, that's actually the critical. So the critical point for the first derivative was c equals -1. Again, that can be a point where you have a local max or a local min. We would have to set up the interval chart for the first derivative to determine that, but it is actually a local minimum. So that's what I see right there. Now, in terms of like the concavity changes at. I'm not doing the best job of actually showing it right here. Okay, but basically for this interval about right there, okay, the graph is, it should have this shape that kind of does more like this. It's like kind of starts and just like goes down like that. So it has like that frown type shape to it. So that would be concave down. It's hard to draw just because the line right here is so close to the x-axis. Okay, concave down. And then here, well, that's like from here all the way to there, that's concave up. Again, if you think of like an extended parabola, the extended parabola would always like open upward. Okay, and that's the second derivative test. The second derivative test is all about identifying intervals of concavity. And if you have a changing concavity, and that's the critical values will tell you. So if you find the second derivative and you identify the NPVs for the second derivative, or identify the values that make the second derivative equal to 0, those are your critical points for the intervals of concavity. And then, like I said, you can identify whether it's concave up or concave down. And then based on that, you can identify whether you have points of inflection or not. Although, again, just be careful, cautious in terms of whether those critical points are also vertical asymptotes. Okay, now what I would like you to do is in the curve sketching booklet, for question number 2, where you have, I think it's about 7 different functions. What I want you to do is, I believe last time I mentioned that I wanted you to create like a title heading that said first derivative stuff. So this time around, beneath that, I want you to write down a column heading that's called second derivative stuff. And I want you to do the following things. So for each of those functions, I want you to figure out what f double prime of x is. 2, I want the critical points or the critical numbers, critical points slash numbers. For f double prime of x. Okay, I want a concavity chart, just like this one right here. So we'll say intervals for concavity chart. And identify points of inflection. And give me both an x and a y coordinate. Okay, and then the next lesson we'll do is we're going to take all the first derivative, second derivative stuff, and some other things that we have learned from previously in math, and we'll try to figure out how we can sketch a bunch of these graphs by hand without the use of the calculator. And I'll talk to you then.